Alright, in this video, I'm going to walk through how this shift register operates, what a shift register is, as well as how we can take our schematic that we see before us here on the screen right now and translate that into a timing diagram. Now, it's very important to understand a few different things about a shift register. First and foremost, what we are doing is we are creating a sort of counter, we'll call it a counter, where when we input a value on JK number 1, which is this flip-flop right here, the output of that chip is going to affect the input of the next chip. So JK1 affects JK2, JK2 affects JK3, and JK3 affects JK4. Now, why is that important? Well, let's talk about one thing, and that is, what is a shift register? Now, in Mr. Stalling's video, he mentioned something called a shift register when he was talking about your calculator. When you type something into a calculator, say I wanted to type in the number 123. As I type in the number 123, the numbers don't erase themselves. They get shifted over. If I type in the number 4, I'll see 1, 2, 3, 4. Everything shifts to the left as I add more digits. That's essentially how a shift register works. It stores data and moves it down a line. Now, don't think of it as a linear line. It's sort of like a loop. It's always looking back at what is our inputs and how does that affect our unique outputs for each and every single flip-flop. Now, looking at the schematic, let's get a few things out of the way first. The most important, this is a negative edge trigger flip-flop. I know that because of this circle right here in front of my clock symbol. Additionally, it has active low, preset, and clear. And those active low presets and clears have been handcuffed. That means that they are never going to come into play here. They are never going to trump our output because they are an active low connected to a high signal. So they will never toggle. So we're not ever going to worry about them in this activity. Also, just like in our event detector, instead of having a clock that oscillates back and forth on its own, like in some of the other activities we looked at, we are controlling the clock here. This is clock high, clock low. And transitioning from high to low will affect our flip-flops. Now this switch here labeled D, it's not D as in a D flip-flop. It's our data inputs because we need some sort of input for any circuit. In this instance, it's a switch that we're calling D for data, not for a D flip-flop. And notice on our first JK flip-flop, our input is straight from the switch and also inverted for K. So J is whatever the switch is, if it's a 0 or if it's a 1, and K will be the opposite of that. And the reason why we want that is for our excitation table. We don't want Q to toggle here. We don't want Q to undergo a no change here. We don't care about these two scenarios here. What we care about is when J is 0 and K is 1, I need to set my output, my Q, to 0. And when J is 1 and K is 0, I need to set my output to 1. And that is how a shift register works. It looks at the unique values of Q to assign the inputs and outputs of each and every single flip-flop. So let's look at that in action. Right now, if I toggle my clock, which you can see I'm doing by pressing the letter C, none of these probes light up. And that's because I'm sending in a data signal of 0. It's grounded right now. So J is 0 and K is 1 every single time this clock triggers. When J is 0 and K is 1, Q is 0. These probes are attached to Q. They're 0 right now because J is 0, Q is 0. When J is 1, Q is 1. So let's see what happens if for one trigger of the clock, So one instance of going from high to low or low to high, what happens when my data is 1? So I'm going to close the switch. Now data is sending a 1 into J and a 0 into K. I'm going to toggle the clock just once. I have just toggled it from high to low back to high. I have toggled it one time. And it only lit up one of my probes. And that is because on the remainder flip-flops, their inputs were still 0. This is sequential logic. It has to flow from JK1 to JK2 to JK3, finally into JK4. And I can see that a little bit more in words here. Start from the bottom and work your way up. J1 and K1 are dependent on our inputs and the clock. J2 and K2 are dependent on the outputs of J1 and K1. J3 and K3 are dependent on the outputs of J2 and K2. And lastly, J4 and K4 are dependent on the outputs of J3 and K3. This understanding is very, very important to understand why this is a shift register. Right now, I've toggled my clock once. If I set my data back to 0 and I toggle the clock again, this first flip-flop is going to go to 0 because J is 0. But the output is a 1 right now. I can see that on this blue probe right here. Because the output is a 1 right now, as I'm about to toggle this clock, that means that this input for J is a 1. So let's back up. Let's start over. I'm going to clear this thing. All I've done is I sent my signal one time with my switch being high, my data being high, my data being a 1. That forced this first flip-flop to be 1. Now my data is open. I'm going to toggle this clock again. Notice what happened. My data was 0 going into J on the first flip-flop, so my output becomes 0. However, it was a 1 when I toggled that clock. So this flip-flop is now saying, oh, J was 1, so Q must be 1. Q is 1 here on this second blue probe. If I toggle the clock again, what do you think is going to happen? Why is this called a shift register? Well, let's watch what happens when I toggle the clock one more time. It shifts the probe down again. And notice, I didn't change anything with D here. I didn't change anything on my data. Now lastly, if I toggle the clock one more time, this blue probe is going to go to the very last spot. It shifts from one spot to the other. And that was for just one sort of pulse, one sort of instance, one action, one snap, where D was 1. What happens if we leave D1 a little longer? Well, let's make it so that 2 probes light up. Right now, I've toggled my clock once. This JK flip-flop said, oh, my data was 1, so Q must be 1. I'm leaving D as 1 here. I'm leaving D as 1, so J is 1. My Q is going to be a 1 still, and also I'm sending a 1 now to JK2. When I toggle the clock, watch what happens. It shifts. It says, great, this guy is dependent on JK1's output. JK1's output at Q1 was a 1, so J2 is now a 1, and Q is a 1. Now I'm going to open this switch again. I'm sending a 0 back to this first flip-flop. If I toggle the clock, notice what happened. This flip-flop was getting a D signal of 0, therefore J is 0, so Q is 0. Nothing happened over here. It shifted those 2 probes. If I toggle the clock again, it's going to shift these 2 probes again. And if I toggle the clock again, it shifts them again until sooner or later, I'm just sending a bunch of 0 values through my flip-flops. This is sequential logic, one after the other. Let's look at that in a timing diagram. Again, we're working our way up from the bottom. Now this D I have put in quotation marks because it is not a D flip-flop. It is just my data switch. Down here I have a clock where all I'm doing is simply pressing the letter C over and over again to toggle from high to low. And now remember, negative edge trigger on my clock. So looking at this, I've gone from low to high. Well, I'm not going to change anything because it's a negative edge trigger. I've gone from high to low here on these squares. I've gone from high to low. So I need to look at what is my data. Well, my data is a 0. When my data is a 0, when J is a 0, and when K is a 1, Q is 0. So back to the schematic, D is 0. When I toggled my clock, which you can see happening down there, D is 0, J is 0, K is 1, my Q output is 0. Great, let's keep going. So I've gone from high to low, nothing happened, low to high, nothing's going to happen because I don't care about that. And in fact, let me draw in the dividing lines here for every negative trigger. This might help. Oops, let me zoom out to do this so I don't mess up my screen. So from low to high, high to low, high to low. I'm just going to keep doing this, high to low. And I'll stop after a few of these just so that we can go back and discuss what's going on here. High to low. All right. So at this first transition of high to low, nothing happened. At the second transition of high to low, my data is now 1. Because my data is 1, because this switch is sending a high signal, J is 1 and K is 0. So I'm going to draw that. Let's draw J being 1 and K being 0. Okay? From high to low. Now look again, from high to low, my data, my switch, is still sending a high value, so J1 is still high and K1 is still low. Now at this transition point right here, between letters I and J, right here, I've gone from high to low, negative edge trigger, and my data is now 0. My switch is now open. So that means that J is now 0, and K is now 1. K will always be the opposite of J. And then we're going to follow this pattern all the way through. D is still low here, so K is high, J is low, and so on and so forth. Oops, not that one there. So it's a matter of spotting these patterns. When these waves get a little sporadic and not as nice and repetitive like they are in this activity or in this example, it can lead to some confusion, but you just have to take the time to work through it step by step. So I have just completed the J1 and K1 timing diagram, and that is only for this flip-flop.